This video is the 2016 Higher Level Section A, questions A3 and A4. So in this question, the drawing on the right shows the axis A1, this one, and the directrix D1, and a focus F for a hyperbola. Hyperbola has an eccentricity of 3:2. So 3:2, that's 2 units along the axis, 3 units perpendicular to it. So I'm going to do 20 millimeters. So 10 millimeters is 1 unit. So out 20, and I'm going to go perpendicular to the axis 3 units. So this here is my eccentricity line. What we need to do next inside in the question is to locate the vertex. So that's the first part of part A. So for all conic sections, so the ellipse and parabola as well, when you have your eccentricity line in your focus, take a line at 45 degrees to the focus until it hits the eccentricity line, and then come back down perpendicular to the axis. That point down here is the vertex. So what we're going to do now is take a line through the focal point. So just do it above. And I'm going to take a number of random lines then, and do one in between the vertex and the focal point as well, or 2. So what we're going to do now, so each time we have one point on our curve, so that's going to be where the focal point touches the line directly above the focal point touches the eccentricity line. That's a point on the curve. What we're going to do for all our other points now is where the random lines that we've drawn, they were all drawn perpendicular to the axis. So I'm going to go parallel to the axis now from where they hit the eccentricity line, back to the line from the focal point, and I'm going to put in that in a different colour so it's a little bit clearer. So lines are going to be projected back until they hit that. Then using our compass focal point from here, swing that back down, putting this point here on the curve. Same below. So same distance down here on the opposite side, that's another point on the curve. So I'm going to do this a number of times. So from this point up here, back to our blue line here, so point for compass on the focal point, pencil up to where it hits the blue line, and rotate that back until back to the original line. That's point on the curve. Mark the same point down on the other end of the other side. Give me that point down here. And I'll do this one up here up on top as well. So from here, rotate this one back down. That gives me a point on the curve. And it may not fit down here. No, so this one goes off the page, so I don't need to worry about that one. Doing the same thing inside, so in the area between the focus and the vertex. So projecting this back in until it hits our new line, rotating from there back or down around, gives me the point on the curve, and you can do the same, mark the same point below. And then finally we're just going to measure from the focal point up to the eccentricity line and mark that on the bottom also. So joining these together, gives us our hyperbola. And where they say here, note it's only necessary to draw one branch. A hyperbola is usually a double hyperbola, so you'll have one branch here and the other branch on the opposite side, only drawing one side of it, so just this side. Part B of this question is to locate point P on the curve, which is 60 millimeters from the focus, and construct a tangent to the curve at point P. So I'm just going to measure a line here of 60. Just so that I can set my compass up with it. So set your compass to 60, check that it's correct. Point your point of the compass on the focus, other point up on the curve. This here is the point P that we're looking for. That's the point on the curve, and construct a tangent to the curve at point P. So one of the constructions that also applies to all conics is if you have point here on the curve, join it to the focal point, and then from there go perpendicular to it. So perpendicular to this line, so taking this line here, perpendicular to it, where that hits the directrix is another point on the tangent. So what you can do is draw from P through that point, and that gives you the correct tangent. So what I did there is joined point P, which is point on our curve, to the focal point, and then I put in a 90-degree angle from that line, from the focus out until it hits the directrix, and that point there is a point on the tangent. So that gives us the tangent that we're looking for. And that also completes question A3. This is question A4. So the drawing on the right shows an incomplete projection of an inclined cube. Complete the elevation of the cube and draw the plan and elevation. Part B is draw the plan and elevation of the smallest possible sphere that would contain the cube. Okay, for this one I would strongly suggest labeling points first, just so that you can kind of keep track of what everything is. So this is A here, that's also A here. Maybe working our way around, C, D, E and F. So F and B, so F is the near one, B is the far away one. I've also labelled G and H. G is the top one, H is the point on the bottom, so this is H, this is G, C and E, so if we're following that here, E is the near one, C is the far one away, and then we've got D. Locating these points then up here in the elevation, this is point B, they've given us H, and they have also given us point F. So this question, the content of what you're asked to do isn't overly difficult, it is just complicated looking. So taking each point in turn is probably the best way of doing this, and doing points that are connected to each other as well. So taking point A first, I'm going to project this one up here. So in elevation it's going to be directly above where it is in plan, and the height is going to be the same as what it is up in the auxiliary view. So taking this, marking that one up there. So this is point A. And A joins to B, so we can darken that one in there. Going to take G here now next, so taking point G, that's projected up along here. We're going to again get our height from the auxiliary view, the auxiliary elevation. Because it's an auxiliary elevation, all the heights are going to stay the same. I'm just putting in a measuring line so I know exactly where that's starting from. That's coming from here. And do that one, and this is just going to make it a bit easier to measure from. So measuring from the XY line, X1, Y1 line up to G, marking that same point up here, that's point G. And I can do, and A also joins to G, so let's join that one up. Coming down the other side, you notice I'm kind of working on the ones that are more towards the front, so it's avoiding the hidden detail for the moment. So F, we already have F here joins to A, so we can join that one up as well. Let's do point E next, so that's the point off over here on the right hand side. Project that from plan to the elevation. Measure the height that is in the auxiliary elevation. Transfer that into the main elevation. This is point E. E, as we can see here, joins to F. E also joins to H, so that's, sorry, no it doesn't. E is going to join to D, this one and under here, so let's do that one next. So taking point D, projecting that one up, measuring the height that is in the auxiliary elevation. this one, get the height right, mark up the height. So this joins to D, this is D, and D joins to H. We can see the dotted line here, D joins to H underneath there. So that completes that part of it underneath here. E joins to G, as I should have said. So this solid line here is E joining to G, so we can darken that one in. And then we just have a point to do at the back. So we already have A, B, F, E, and D. We have G and H, so C is the only point that we're missing. C is here at the back, so everything coming from C will be a hidden detail line. It's somewhere up above there. Measuring the height, it's at the same altitude as E, so I'm measuring this in the auxiliary elevation, marking that there as C. Now C joins to B, so we can see C joining to B, so that's a hidden detail line. C also joins to D, we can see that joining here. And again, hidden detail line, and C joins in plan as a solid line to G, so but it'll be hidden detail, we can't see that up here, so it's a hidden detail line running up along that way. So that completes the elevation of the cube. So what you're asked isn't overly difficult, but you should definitely label your points, get those labeled correctly to start with, then this becomes a bit easier. Final part of this is to draw this, the plan and elevation of the smallest possible sphere that would contain the cube. So what sphere can we put around this that the cube will fit into? So it needs to be the smallest one, so it's going to be touching it somewhere. For this you need to look closely at it and recognize that G and H are directly above each other, they're vertical, which means that a line joining G to H here in the elevation would be a true length line. And also means that it's the longest possible line inside in the cube. So G to H. So what we're going to do is we're going to bisect that line. So if I bisect this line, close the other compass. So swing an arc here, same from the top, swing an arc here. This is the midpoint between, it's halfway between G and H. So I can put this here and here. And then this is the largest possible sphere. So get my hands out of the way. That fits, that will contain the cube. So all we've done is, again, this looks more complicated than it actually is. You need to recognize that G and H they're directly above each other, they're vertical, which means that this line here is going to be a true length. So we're looking straight in at it. And it also means that it's the longest possible distance inside in the cube. So if you bisect that distance, the midpoint of that is going to be halfway, and it'll be the center of the sphere that will contain the cube. So the sphere has to go around the outside. So G, so from this point to G or this point to H is going to be the center or the radius for that sphere. And that completes this question and the A3 and A4.